Okay, let's start from where we stopped last time. Actually, we started with the transient conduction, and if you remember, we talked about an approximation which makes our life easy. It was a lumped capacitance approximation. Okay, after going through the lumped capacitance approximation, our heat diffusion equation reduced to only temperature dependent with time. And when you have just temperature dependent with time, then it is just conduction equals to convection, like that, and we get the main equation. So our main equation becomes these were the equations that we got: rho Vc upon HAS ln theta I upon theta equals to time, or theta upon theta I equals to exponent negative HAS upon rho Vc multiplied by time. Okay, these were the equations that we got, and after that also we got this equation for Q. For Q, it is equals to rho Vc theta I into 1 minus exponent negative t upon tau. Okay, and where tau is equals to rho Vc upon HAS. Okay, so these were the things that we came up with last time. And then we also just said that this lumped capacitance approximation is applicable only if the resistance to conduction is very small. And how we determine that the resistance to conduction is very small? We determine the Biot number, and the Biot number was okay. The Biot number was HL upon K, right? So that is the thing, and it should be less than 0.1 if this lumped capacitance analysis has to be applied. And where L is the characteristic length, and for plane wall it's in the direction of the heat flow. For the long cylinder it's R by 2, for a sphere it was R by 3. These are the things that we determined last time. What else? We had another number, the Fourier number, which determines that how much is the energy transported compared to how much is the energy stored. Okay, and Fourier number had the formula alpha t upon LC square. Okay, so that's the formula for the Fourier number. Okay, now we come over to a numerical. Okay, we have a thermocouple junction. Now probably you should know what is a thermocouple. Thermocouple is what? It is a device to measure temperature. Okay, how does it work? Probably you would have gone through in the course of measurement and data acquisition. Okay, so basically it is a device which, if you put it any place, it will tell you the temperature. You can get an electronic reading of how much temperature you have at that position. Okay, so we have a thermocouple junction. Junction means it's the point. Okay, which may be approximated as a sphere. Now this junction, they are saying that it's like a sphere. It's like a small ball. Okay, is to be used for temperature measurement in a gas stream. So we have a gas stream, somewhere gas is flowing, and we need to measure the temperature of that gas, and this thermocouple junction is to be used. The convection coefficient between the junction surface and the gas is this. So H is given. So H between this junction and the gas stream is given. It's 400 watt per meter square Kelvin. And the junction thermophysical properties are, K is given, thermal conductivity of the junction, the material for the material of the junction is given. C is given, heat capacity, and rho is given, density. So these three properties are given for the material of the junction. Okay, so we have, what properties do we have? We have H here, we have K here, we have C here, we have rho here. Okay, determine the junction diameter. Okay, junction diameter is not known. this is something we need to find out. What is the junction diameter? Okay, and needed for the thermocouple to have a time constant of 1 second. So time constant is given. Remember, this is the time constant. Okay, so this is given. Time constant is 1 second. Okay, so but we need to know what should be the size of this junction so that it has a time constant equals to 1 second. Okay, if the junction is at 25 degrees centigrade and is placed in a gas stream that is at 200 degrees centigrade, how will it take for the junction to reach 199 degrees centigrade? Okay, so junction is initially at 25 degrees centigrade. So we have the initial temperature of the junction. Ti is 25 degrees centigrade. Okay, and the gas stream T infinity is 200 degrees centigrade. Okay, and we need to know that how long will it take until the junction will reach 199 degrees centigrade. That means approximately 200 degrees centigrade. Okay, how long will it take to reach that temperature? Now the first thing is that we need to determine the diameter of the junction. Okay, now the thing that we have studied so far, first of all, it's a problem of transient case. How do we know it's a problem of transient case? We have a junction, its temperature was initially 25. Now as the gas stream is passing, the temperature of the junction will rise. So with time, temperature is changing. It's not a steady state. With time, temperature is changing. One thing is clear by the question, it's a transient state problem. Now for the transient state problem, we can have a problem where lumped capacitance analysis is applicable. We can have a problem where it is not applicable. We don't know. We can know it only by considering the byte number, right? So let's try to do that. Let's try to find out the byte number for this case. Okay, byte number is what? HL upon K, right? Is H given? H is given. What about K? K is also given. What about L? L will be the characteristic length, and this junction is considered as a sphere, right? So for a sphere, LC should be R upon 3, right? We determined that last time. Okay, or in terms of the diameter, it could be written as D upon 6, right? But we don't know the diameter. That is the thing that we need to find out. If we don't know the diameter, we don't know the characteristic length. If we don't know the characteristic length, we cannot know what is the byte number. If we don't know the byte number, we cannot know whether the lumped capacitance analysis is applicable or not. So we cannot proceed in any way. But let's assume that lumped capacitance analysis is applicable. Let us assume right now. Okay? Let us assume right now, and we find the diameter. Then we will find the byte number. If our assumption was correct, the byte number would be within our range. If our assumption is wrong, the byte number will be out of the range. It will be greater than 0.1. Okay? So let's assume that, because all these formulas that you have seen here, written here, are applicable only for the case of lumped capacitance analysis, if the lumped capacitance analysis is applicable. If that approximation is applicable. For that we need to know the byte number, but we don't know the byte number because we don't know the diameter. So we cannot proceed in any case. What we can do is that we assume that it is applicable. And after that find the diameter, and then use that diameter to find out the byte number. If our assumption was correct, the byte number would be less than 0.1. If our assumption is wrong, byte number would be greater than 0.1. Okay? So let's assume that lumped capacitance analysis is applicable. Okay. Now if the lumped capacitance analysis is applicable, now we need to determine the diameter. Okay. So what do we have? We have this time constant, right? The time constant is given. Time constant is what? It's 1 second. Okay. Now this is the time constant, right? This is time constant, and it is 1 second. Okay. So we know tau. Do we know density? Density of the material is given, right? So we know rho, we know h, we know c. These are the three properties that we have. Okay. Okay. We don't know volume, but we don't know the surface area. But that is the formula for the characteristic length. Characteristic length is equals to volume over surface area. right? And for the sphere, when we place the values of the volume and the surface area, it comes out to be diameter upon 6 or r upon 3, right? So I can replace, so now I can write here tau is equals to rho c upon h, these are the three things given, and then v upon a I can write here as diameter upon 6. Is it clear? Because this is a sphere, v upon a as for the sphere is d upon 6 or r upon 3, okay? So now in this case, I know everything except d. I can find what is the diameter, okay? Now once you do this, okay, once you find out, the diameter comes out to be 7.06 into 10 to the power minus 4 meter. It's a very small diameter that comes out, okay? Now what we do is that we place this diameter in this formula here, so that we know the byte number, and we should know that whether our calculation was correct or not. Because this diameter was found based upon the formula for the time constant this. But this formula came because only if the lumped capacitance analysis is applicable. So we need to check whether our calculation is correct or not. Okay. So now what we know, what we do is that since we know diameter, we place the diameter here, we get corrected length. Oh, so not the corrected length, sorry, the characteristic length. Once we know the characteristic length, now we place it in here, we find out the byte number, right? So after finding the byte number, it comes out to be 2.35 10 to the power minus 3. What do you think? Do you think this value is greater than 0.1 or less than 0.1? It's less than 0.1. So if it is less than 0.1, that means it's applicable. That means our diameter is correct. Okay? So we went other way around to solve the problem. Okay, so that means our diameter is correct. So that was the first part. We determined the diameter. This is now find out. This is now done. Is it clear?
Yes, it is.
Okay. Now let's move towards the second part. If the junction is at 25 degrees centigrade initially, okay, and placed in a gas stream that is 200 degrees centigrade, how long will it take for the junction to reach time? What is required to be found? How long? Time is required to found. Okay. Time is required to be found. So which formula determines the time? The first one. First one. Time and time constant. Time constant is a constant. Okay. Time constant is a constant. That means, suppose if I want to say that how long will it take for you to travel 1 kilometer? Now that's a time constant for you. How long will it take for you to go to an engineering building? Now this is the time required. But time constant is fixed for you. Your is based upon your speed. Okay? So it's a constant for you. Your time, suppose you take 1 minute to travel 1 kilometer. Now that's a time constant for you. Whether you want to travel from here to Dammam, whether you want to travel from here to Riyadh, whether you want to travel from here to your home, time constant remains same for you. Okay? Time will change if the distance changes. Time constant will remain same. Is it clear? So it's like that. So time constant was given. Time constant depends upon the material property. For example, time constant will be different for me, for you, will change if we change the person here. Okay?
So the question you will state that this is a time constant?
Yes, you see here, this is time constant. Okay? Now you are required to find time constant based upon the material. That's why you see here in the formula it has density. Density is of the material. Specific heat is of the material. Surface area is of the material. Volume is of the material. It's a material property. You change the material, time constant will change. Is it clear? So now we need to find out the time for it to reach from 25 degrees centigrade to 199 degrees centigrade. Okay? So now if you put this formula, okay, we already know the time constant. This is time constant, right? So this is something we know. Okay. Now let's talk about this. Time we need to find. Ln theta I upon theta. Theta I is what? Ti minus T infinity. Do we know Ti? We know T infinity. And theta is what? T minus T infinity. T infinity we know. T is the temperature which we want to find. A temperature for which we want to know how much time it will. So it will be 199. Okay? So if we put here 199, so it's going to give us the time. Now somebody might think, okay, look, the thing is that when we do the calculation, okay, so the time comes out to be 5.2 seconds. So what does this mean? This means that this junction will take 5.2 seconds to reach 199 degrees centigrade. So suppose there was a gas stream and you put the thermocouple in it and you remove the thermocouple from the gas before 5 seconds, it will give you the wrong temperature, because the thermocouple was supposed to give the temperature of the stream. But for giving the temperature of the stream, the thermocouple should reach the same temperature. Then it will give you the right temperature of the stream. So the time for it to reach 199 degrees centigrade is 5.2 seconds. So you put the thermocouple, you remove it in 2 seconds. It will give you a wrong temperature, because it itself has not reached 199 or 200 degrees centigrade. Okay? So this is the significance here. You should know that for how long you can place it, what should be the minimum time that you should place it in so that it will give you the right temperature. Okay? Now the thing is that, now one might think that we are finding out the temperature of the gas stream, and the temperature of the gas stream, if it is 200, then we should find our T should be 200. Why we put 199, right? So suppose if we put here 200, what will happen? That will become T infinity, right? And something upon 0 is infinity. Okay? So this becomes a singularity problem. It cannot be solved here with this formula. So with this formula, you have to be within the limits of T infinity, below it, slightly below it. Imagine it. So because we are finding the time, so 5.2 seconds means reaching 199 means approximately reaching 200. Yeah, it will give you 200. But so if you wait till 6 seconds, you will get the right temperature. Okay?
If I proceed more, it will not exceed.
It will obviously, maximum temperature it can reach is T infinity. Okay? That's the temperature of the gas stream, and that is the temperature it will give. Okay? So you wait till 6 seconds, 10 seconds, 15 seconds, it will give you 200. But if you wait less than 5 seconds, it will give you wrong temperature. Is it clear? Anyways, that was the problem. Is there anything that you did not understand in the solution of the problem? Okay.
I did the previous slide. The D is 6 HT over.
D is 6h tau over rho c. Okay. D will be what? Okay. Actually, when I proceed on the board, I proceed very stepwise.
Yes, yes.
From what you have learned in the formulas. When they solve it at an instant. Everything in one step is there. Okay. Yeah. So it is the same thing here, but I moved it in a regular way. They moved it in one step. Okay, so this topic is over. Let's move towards the next topic.
I think the way of solution looks easy. 4 steps.
Yeah, it's actually not about the steps. It's about the understanding. Yeah.
Take this.
Okay. Let's move towards the next case. So we're talking about the transient conduction case, and initially we solved the problem using an approximation which made our life easy. The approximation was that the material behaves like a lump and there are no temperature gradients within the material. So it's in the space of the material there is no temperature gradient. So there are no space effects. Okay. Now let's say that assumption is not true. Let's say we have a material for which Biot number is greater than 0.1. Okay. So we cannot apply lumped capacitance approximation. So that means our life becomes complicated, more complicated. Temperature is a function of time, temperature is a function of space, x, y, z, t. A very difficult differential equation becomes, and solution of it becomes more difficult. So now the special effects are there. Last time we ignored the special effects. Now the special effects are there. So these are there, special effects. Suppose if it is a one-dimensional case, we try to simplify ourselves. It's not a three-dimensional heat transfer, it's a one-dimensional case. So we have dou y square t by dou x square equals to 1 upon alpha dou t by dou t. This will be there, okay, if we simplify the heat diffusion equation, but still solving it is a bit difficult, because now we just don't need the boundary conditions, because it's a function of time as well, so we need the initial conditions as well. We have the boundary conditions are different thing, initial conditions are different thing. So we have to put the boundary conditions as well as the initial conditions. We are not going to go through, I'm not going to go through the solution procedure here. Okay, it is done in the book, and if you want to go through it yourself, you can go through it yourself. But anyways, after going through the solution procedure, what we end up is that our theta is a function of summation n equals to 1 to infinity c power n exponent negative eta square Fourier number cos eta power n eta subscript n x star, where the eta and c are the constants, and these are the Bessel function constants, and there are about 2-3 pages in the appendix given about the Bessel function constants. Okay, if we consider so they have the different order approximations, and are the order approximations. So we can have first order, second order, third order, fourth order. This is all differential equations, deep differential equations. Okay, the solution procedure of it is very complicated. Anyways, so we are not going to go through it, but this becomes the general form of the formula that we have if we have the special components with us, if we have the special effects with us. Okay. Now the thing is that we can solve only for the first approximation if we apply only the first approximation. So first approximation constants we have to apply, and then it will be valid only for limited number of Fourier number. Okay. So if the Fourier number is greater than 0.2, then first order approximation is applicable. Okay. And if the Fourier number is greater than 2, then this becomes the solution. Okay. So we have theta star equals to C1 exponential negative eta 1 square Fourier number into cos eta 1 x star, where eta 1 and C1 are the constants here. Okay. And this is given in table 5.1, which is a part of your which is there in your book of tables. Okay. So constants for plane wall eta 1 and C1, for infinite cylinder eta 1 and C1, for sphere eta 1 and C1 are given. These are the constants. Okay. And based upon the Biot number. So you find the Biot number, based upon the Biot number you will find these etas which you are going to put into this equation. Okay. In the book view, they have given the problems for the plane wall, infinite cylinder and sphere, all three, but we here in our lecture we are going to solve only for the plane wall case. Okay. For the other cases, if you want to see the solution, and the problems are there in the book, and you can go through it yourself. Okay. Anyways, now what are the formulas? What are the end results? We are right now here concerned with the end results. I'm not going to go through with you with the derivation things. They are very long, very complicated, but things you might have covered in differential equations, okay, or you should have covered there. Okay. So anyways, so we have these are our end results. Okay. So what do we have in this case? We are supposing that we have a plane wall, and in the plane wall, in the plane wall we have a hot fluid on one side, we have a cold fluid on the other side. We have spatial effects. Okay. So we have spatial effects in this wall. This means that the temperature, there is temperature gradient within the wall. Okay. So when you have temperature gradient in the wall, so that means temperature is not constant. This is not the case now. Previously it was like this. Temperature was same. Now we have a temperature gradient. So whenever we have a temperature gradient, we will have a specific plane where the temperature gradient becomes 0. Okay, and that specific plane could be considered as an adiabatic plane, and that plane we consider as our reference point. Okay, so that is the plane where we put our x0. Okay, so here we put the values not in terms of the x, in terms of x star, where x star is what? X star is x upon L. It's a dimensionless length, dimensionless distance. L is the length from the adiabatic plane to the edge, to whatever the edge you have. So here you have x from here 0 to L or 0 to L in this direction. So x star is x by L. Similarly, instead of putting theta, we put here theta star. Okay. So theta is what? Theta is t up minus t infinity. Okay. And theta star will be what? Theta star will be t minus t infinity divided by t initial minus t infinity. Okay. T initial will be a kind of a constant here in any case. Okay. So we are talking about transient case. So transient case, there will be an initial temperature, there will be the final temperature. Okay. So we are finding theta star as a function of x star. Okay. Anyway, so what formulas do we have here in the end? Let me show that. So we have one formula, this, that theta star is equals to theta naught star into cos eta 1 x star. Okay. So theta star, as I told you, is the temperature, dimensionless temperature at that point. Theta naught star. Theta naught star is basically what? Theta naught star has a formula, and that formula is theta naught star is equals to C1 exponent negative eta 1 square Fourier number. Okay. Now you need to understand what does this eta naught means. Okay, eta naught means the temperature of the adiabatic surface. Adiabatic surface is normally the surface where you have the highest temperature. That is the point where the temperature gradient becomes 0, but the temperature becomes highest. Okay, so that's the point where the curve, after becoming maximum, starts becoming minimum. Okay. So that's the point where the gradient becomes 0, but the temperature is the maximum. So theta naught star is like finding the maximum temperature. Based upon the maximum temperature, you find the actual temperature at any point other than the adiabatic surface. Okay. So we have this formula. Then we have a formula here for Q. Suppose we need to find out, because there are two things that we need to find normally: temperature distribution, T as a function of x, and heat transfer. So that's the T as a function of x, because T we put as theta. Theta is a function of x star. X star, I told you now, is x by L. Okay, so theta is a function of x, but it uses the maximum temperature, for which the formula is this. This is exponent exp. Okay.
What is the symbol for eta?
Eta. Eta is a constant. Eta. Okay. Eta is a constant. Okay, so these are the Greek symbols. So it's a constant, and for these constants are the first approximation constant given in table 5.1, which I told you you have to find it against the Biot number. So you have the Biot number, find out eta, find out C. So C and eta are the first approximation constant. You get it from the table 5.1 against the Biot number. Okay. This whole problem becomes so complicated and things like that because now you have spatial effects. Okay. Now the temperature is changing with time and with the space. Now it's not just the boundary condition which will solve your problem. You need initial condition and boundary condition together in the solution. That is why things are becoming like this. Anyways, so this determines the temperature, right? This temperature as a function of x. This determines that. Now the second thing, as I told you, we need to find out is the amount of heat transfer. Okay, so amount of heat transfer, this formula. Okay, so Q upon Q naught equals to 1 minus sine eta 1 upon eta 1 theta naught star. Okay, so that's the actual temperature, that's the actual heat transfer, but this is the maximum heat transfer. So for maximum heat transfer, the formula is Q naught, that's the maximum heat transfer. Q naught is equals to rho CV Ti minus T infinity. That's the maximum heat transfer. Anyways, these are the 4 formulas which are considered to be the main formula for you in the solution of the problems. Other formulas written here are used to derive these in the steps of derivation of these. Okay, and the complete derivation itself is very big and it is there in your book. So if you are interested to go through with it, so you are most welcome. Okay. Okay. So it's going to give you a revision of your differential equations as well. Okay, and you might be enthusiastic. I need to learn more. Okay. Okay. So let's have a numerical problem related to it. Okay. Consider a steel pipeline that is 1 meter in diameter. Okay. Now this is an interesting case. We put the formulas for only the plane wall. We did not put any formula for the cylindrical rod or for the sphere. Okay. But we are considering the case of a pipe. Okay. But the thing is that look at the diameter of the pipe. 1 meter. 1 meter diameter is too big. That much big pipe. Okay. That much big pipe means if you consider the wall of the pipe, if you see it from very close, it will look like a plain wall. But you have to be very close. Okay. Don't be too far away, otherwise it will look like a pipe. Okay. So if you look it from very close up, so it will look like a plain wall. Okay. So consider a steel pipe AISI that is 1 meter in diameter and has a wall thickness of 40 millimeter. Okay, so that diameter is given. That's the diameter. That's the wall thickness, 40 millimeter. Okay, the pipe is heavily insulated on the outside. So we have this is our pipe. Okay, and it is heavily insulated on the outside. So here we have insulation. Okay, that's the insulation on the outside. Okay, and before the initiation of the flow, the wall of the pipe are at a temperature of minus 20 degrees centigrade. So this is the pipe, and obviously there is going to be some fluid flowing through it. But before the fluid started to flow, the pipe temperature was minus 20 degrees centigrade. Probably you are in Canada, okay, where the ambient temperature is too low. The pipe is initially at minus 20 degrees centigrade. We love to have it in here, but we don't have it in here. Okay. So initial temperature of the pipe is minus 20 degrees centigrade. With the initiation of the flow, hot oil, consider hot oil, 60 degrees centigrade. Here we have water coming at 50 degrees centigrade in our houses. So they have the hot oil coming at 60 degrees centigrade is pumped through the pipe. Okay. So this was initially temperature was negative 20 degrees centigrade, and from this pipe they started pumping oil, and the oil was very hot, 60 degrees centigrade. Okay, Sometimes I take a shower here in the noon, it's like it feels like 60 degrees centigrade. Okay. Creating a convective condition corresponding to H is given at the inner surface of the pipe. Okay, so that's obviously when the oil flows through the pipe, so there will be convection at the inner surface. Heat will be transferred from the fluid to the pipe, right, at the inner surface. So this H is given, what is there at the inner surface. Okay. What are the appropriate Biot and Fourier numbers 8 minutes after initiation of the flow? So they started the pump and the oil started to flow through it, and now after 8 minutes has passed, what is the Biot number and what is the Fourier number? First of all, they wanted to find this thing, and that's the right sequence. In any case, in any transient problem case, the first thing you should determine is the Biot number. The Biot number is the thing that will give you an analysis that how you should proceed with the problem. Is it a problem that you can proceed through lumped capacitance analysis, or you have to make your life a hell? Okay, so the first thing is that the Biot number. Biot number decides your future, decides the future of the solution of the problem. Okay, so the first thing is that they want to know what is the Biot number and Fourier number 8 minutes after. Fourier number, look, the formula for Fourier number has time. That's why they said 8 minutes after the initiation of the flow. But for the Biot number, you don't need time. Okay, its time is there only for the Fourier number. Okay, so we have the formula here for the Biot number. It's HL upon K, right? H is what? Is given, right? H is given. K is given. K is not given, but it is said that this is AISI 1010. Take the average temperature. Okay, it was minus 20 degrees centigrade the pipe, and the flow was 60 degree. So you can take the average of the temperature and find out the K at that average temperature. Okay, so you have the K as well now. Okay, what would be the length here? Well, the heat is flowing in which direction? Across the thickness, right? So the length will be the thickness here. This is a plane wall actually. I told you that you see it from very close view. It's a plane wall. Okay, so L here would be the thickness. Okay, in the plane wall. So now you know the thickness as well. It is 40 millimeter. Okay, so you know everything to find out the Biot number, and you'll find out the Biot number. What about Fourier number? For Fourier number, you need alpha. Okay, so alpha you can get it because alpha is K upon rho Cp. Okay, so alpha is equals to K upon rho Cp, but all the things K rho Cp, you can get it from the table based upon the temperature you are considering. Okay, so all the three things you get it from the appendix. Okay, time is given. Time is given 8 minutes, but make sure it's given 8 minutes. Basic unit is second. Okay, so convert it into second, and then LC again length is, you see it from very close view, and this this is the plane wall, so it's the direction of flow of feed, that is just the thickness. So LC square. So you know all the things here. So you can find out what is the Fourier number.
Will be the thickness also?
Yes, where is the thickness? LC is the characteristic length. L is out, it's LC here. So where were we? Okay, we said that we find out the Biot number. We said that we find out the Fourier numbers. Okay, so now let's look at it. When we find the Biot number, we were so unlucky that we got the value 0.313. So that means it's greater than 0.1, and we cannot apply lumped capacitance analysis. 0.2 is not okay as well. 0.15 is also not okay. 0.11 is also not okay. It should be less than 0.1.
But at 0.2, that means the first step?
No. Oh yeah. No, but that was for the Fourier number.
Okay.
That was for the Fourier number. Okay. Is it clear? So now, huh? There's a Biot number 0.313. I was hoping that we get less than 0.1, so our life get a bit easy, but unfortunately, this is how life is. So our Biot number is 0.313. That means lumped capacitance cannot be applied, and we have to.
Even if it's 0.13.
No.
0.1.
Yeah, 0.1 you can apply. 0.1 you can apply. But 0.101, no. Is it okay? So the Fourier number, once we did the calculation, it comes out to be 5.64. Okay. Anyways, we determined the Fourier number, we determined the Biot number. Okay. That was the first part. Now what's the second part? Second part is that at t equals to 8 minutes, what is the temperature of the exterior pipe surface covered by the insulation? So we need to find the temperature of the exterior pipe surface which is covered by the insulation. Now remember, for this case we determined that there will be a surface where it's like adiabatic, where we'll have the maximum temperature. In this case, the outer surface is the adiabatic surface where we have the maximum temperature because the insulation is applied. Okay, so that's the surface where the temperature gradient will be 0 for our case here. Okay, so if we look here, so we need to find out the temperature basically. So this is now the maximum surface, adiabatic surface, maximum temperature surface. Okay, so we need to find T naught. Okay, we need to find T naught. T naught, as I told you, naught was for the maximum. Maximum occurs at the adiabatic surface. Okay, so in this case, although here in the plane wall, our adiabatic was at the center. Now here, if we consider this as a plane wall, if we look at from very close, so our adiabatic is not at the center. Our adiabatic is here at the top, right? Our adiabatic is at the top, and then we consider it that this distance is L, length, the thickness. Okay. So we have here half case with us. Okay, adiabatic to the outer surface. Now what do we need? We need to find T naught, right? We need to find temperature T naught. So that means if we want to find T naught, it's like finding theta naught star. Okay, so by this theta naught star we can find what is T naught, right? Okay, so let's find theta naught star. How can we find theta naught star? We need what other things? We need Fourier number. Do we have Fourier number? We have calculated already Fourier number. Okay, because we need to find temperature after 8 minutes, and we calculated Fourier number after 8 minutes. So that means it's the same Fourier number that we'll use, because if the time change, Fourier number will change. Okay, Fourier number depends upon time. Anyways, this is the same Fourier number that we'll use. Now we need just these two constants, C1 and eta 1, right? We can get these constants from the table, because in the table you have the Biot number, and based upon the Biot number you have these two constants. Okay, but for the plane wall. Okay, so we'll get this from the table, and so now we have C1, eta 1, F naught, Fourier number. We know all these things. Substitute the values, you will get theta naught star. Okay, so now we have theta naught star, but I told you what is theta naught star. Theta naught star is basically T naught minus T infinity upon Ti minus T infinity, right? So we need to find T naught. Okay, we know theta naught star, we know what is T infinity, that's the oil temperature, and we know what was the initial temperature of the pipe, minus 20. Okay, so we know all these things, so we can find what is T naught. Is it clear? So that means once we solve it like this, so we'll get that after 8 minutes, the pipe outer surface is at 42.9 degrees centigrade. Okay, so we had the pipe initially at minus 20. We started oil to make flow through it. The oil is at 60 degree. So the temperature of the pipe will rise, and the outer surface of the pipe after 8 minutes will be at a temperature of 42.9 degrees centigrade. Is it clear? That was the second part that we wanted to solve. Is there anything which is not clear? Please ask.
How do you know this will find T naught?
How do we know we need to find T naught? It is said that find out the temperature of the outer surface. In this case, our outer surface is insulated. Since it is insulated, so that's the adiabatic surface. T naught is the temperature of the adiabatic surface. Is it clear? T naught is the temperature of adiabatic surface. Part 2 is done. Is it okay? Is there anything that you need to ask from part 2? No?
In material, quantify the material. There's something on there. That was tricky to find it. Like,
That's using the tables.
Eta and
Eta and constant C1. Yeah, use it from the tables 5.1. Get the byte number, from the byte number, find out the eta and constant. So it's like this. So you have this table. This is just the start of the table, this one-page table, I think. So from the byte number, whatever byte number you have, corresponding to that, find out eta, find out C for the plane wall.
What's in radian or what?
It is in radian because it's as an exponential of this thing, it's a cos of this thing. Okay, its unit is radian. That doesn't mean that you have to. There's nothing that makes you complicated.
how will I choose the value from the table? I got the BI.
Yes,
From where?
you calculated BI
Oh,
byte number. You calculated, right? That's the thing based on which you decided that it's going to be the special effect case.
The BI is equal to 0.303.
0.313.
1, 3. That means I have
Yeah.
to make interpolation.
Yeah.
Or use 0.3.
No, you make interpolation. Okay. Is it clear? Is it clear? Okay. Let's move towards the third part. What is the heat flux to the pipe from the oil at T equals to 8 minutes? So we need to find Q, but not just Q, heat flux. So what do you think when the oil is flowing through the pipe, where will the heat flux occur? From at the inner surface, right? So at the inner surface, heat flux will occur, right? So what's the formula for heat? Heat is Q is equals to HA delta T, right? Or delta T is what? T minus T infinity, right? T minus T infinity, right? This is basically Q is equals to HA delta T. But we do not want to find Q. We need to find heat flux. So let's remove area from here. Okay. So that's the heat flux now, right? So now we need to find heat flux. This is the thing that we need to find. Do we have H? H we have, given in the problem, right? So H we have. Do we have T infinity? That's oil infinity temperature. That's we also have. But do we have the temperature T? We need T after 8 minutes, but this T should be at the temperature of the inner surface, not for the outer surface. We found out the temperature of the outer surface, T naught. But the heat transfer here will occur at the inner surface. So we need to find the T for the inner surface, right? So if we find the T for the inner surface, we can find what is Q flux. Now finding T is like finding theta. Finding T is like finding theta. So here like finding theta is like this, right? So we already have theta naught star. Theta naught star we already found out, right? So here, okay, what will be, if we already have eta 1. Eta 1 we already have, because for finding theta naught star we already got eta 1 and C1. Okay. What about X star? X star is X over L. But in this case, if this is our adiabatic surface, so that is our reference point x0, and here X is L. So we want to find X at L. So L upon L becomes, so X star becomes 1, right? Because our X is at the adiabatic surface. So it starts from there, X is 0 at there. And then we move towards the outer surface. Okay, so since we need to find the total outer surface, so that means consider this as the L thickness. So our x star is x upon L, where x is L, so L upon L is 1. So in this case it is 1 here. This thing is also known. Okay, so now we know all the three things here, right? We know eta 1, we know x star. This we already determined. Okay, this is the same here. Okay, so now once we know theta star, we can find theta, because theta star is basically what? T minus T infinity upon Ti minus T infinity. So we know T infinity, we know what is Ti, we know what is theta star, we can find what is T. Is it clear? So once we go through it, so we will get that our temperature comes out to be 45.2 degrees centigrade. And once we know this T, our objective was not to find T. Our objective was to find heat flux. So now we can put the value of T here, and we can find what is heat flux. So putting the value of T here, we'll find what is the heat flux. Is it clear?
Why they choose the Q for convection? Because this plane one, we need to choose the convection.
Actually, we are not finding what is the heat flux from the inner surface to the outer surface. We are finding what is the heat flux transferred from oil to the inner surface. We are finding out what is the heat flux from the oil to the inner surface. Okay? That's why we are choosing the convection. Is it clear? Okay, so now what else do we need? So part 3 is also done. Now the last part. How much energy per meter of length, pipe length, has been transferred from the oil to the pipe at T equals to. So we need to find how much is the total energy transfer. Okay. So how much is the total energy transfer is Q, right? But for using this Q, I need to know first what is Q naught. Okay. Q naught is the maximum heat transfer. Okay, so Q naught is rho C V Ti minus T infinity. You know what is T infinity? You know what is Ti? You know what is rho? You know what is C? And V is the volume of the pipe. Okay, so because you know the diameter, you know the thickness. Okay, so but you don't know the length, but we need energy per meter of the pipe length. Okay, so you don't need to use the length. So anyways, you know what is Q naught. Based on if you substitute Q naught here, already you know what is eta, already you know what is theta naught star. These things you already determined before. So just substituting the values and find out Q. Okay? That's Q upon Q naught, where Q naught is this thing. Okay? So substitute the values and just find the value, find the answer. That's it. So in this way, this problem is done. Is there anything that you do not understand in the solution of the problem? Okay? The problem uses these formulas. These formulas are for the plane wall only for the case where we have the temperature gradients within the body. Lumped capacitance cannot be applied. Okay. Now this is for the case of a plane wall. That was the case of the pipe, but we considered the case of the pipe as that of the plane wall. Okay. By considering an approximation of the plane wall, we solved for the case of the pipe. But we also have the solutions for the pipe case as well. We also have the solution for the sphere case as well. It's not done in the slides, but it is there in the book. If you want to go through it, you're most welcome. Okay? And if you have any question in those, you can come to me anytime. Okay? I'll be more than happy to answer. Okay. So with this, we complete our chapter number 5. So if you see here in chapter number 5, well, just to summarize, we started with the transient problem. First we made an approximation, and the approximation made our life very easy. We got some formulas. These formulas are comparatively more easy to use, and we solved a problem based upon that approximation. But the approximation uses byte number less than 0.1. However, if the byte number is not less than 0.1, we cannot use that approximation. Then special effects will be there. Problem becomes more and more complicated. Okay, so we only solved a small case, first approximation, only for the plane wall case, and we got these 4 formulas. These are the end results. We use these end results to solve for the case using plane wall approximation. Okay. However, for the cylinder, for the sphere, we did not use. Other than that, we also have the numerical approach, but we have not covered the numerical approach for the case of the transient. But it is still there in the book. Okay. The more you eager to learn, the more you can go through it. Okay. So, is it clear? So now we are done with the conduction. One-dimensional steady state, two-dimensional steady state, and then after that the transient conduction all together. We started with chapter number 2 where we developed the main equation for the heat diffusion. That was the main equation which we have been using throughout till this chapter. Okay. So our conduction is over, done. Khalas, khalas. No. Now we are going to start with convection after a break in chapter number that is chapter number 6. Okay. So chapter number 5 is done. So you have a small gift as well. Okay. So we are going to start with chapter number 6 after a small break. Okay, so let's continue. Let's move on with our life. Okay, so we are done with the conduction. Okay, and conduction was comparatively a smaller portion than the portion in which we are going to go into now. Convection is a big portion, and it has many formulas, tons of formulas. But the good thing about is that in convection, since you have a lot of empirical formulas, so those formulas are like provided to you in the exam. And the only thing that you need to know is that what kind of problem you have, so which formula should you select, and then how you apply the formula. That's it. Okay. So it's like select the correct formula and apply it. It's like that. But anyways, in chapter number 6, we will have an introduction to convection, like we had the introduction to conduction. Okay, and from here onward we'll move. In chapter number 6, you have some of the things here which are actually a part of fluid mechanics, not heat and mass transfer. So we're gonna move a bit quickly through that. Okay. Then in chapter number 7, inshallah, from there onward the real convection works start. Okay. So let's start. Chapter number 6, the topics that we are actually covering here. From here onward, or even before, we are not covering everything in every chapter. Okay, there is a whole lot of material, and part of it we cover, and some part we leave. So, anyways, the things that we are covering is placed here, the coverage for this chapter. So, introduction. Convection includes energy transfer by both the bulk fluid motion, which was the advection, and the random motion of fluid molecules, which is the conduction or diffusion. That's in chapter number 1 we studied that. Okay, so that's a heat transfer by the actual motion of the molecules, and this is convection. Now let's start with this chapter. Let's study the concept of velocity boundary layer. Okay. Now suppose we have a uniform flow of air. So air is flowing at a uniform velocity. Uniform means no change with distance. Okay. So if I see the velocity here, it's let's say 10 meter per second. If I see the velocity here, also 10 meter per second, here also 10 meter per second, in the whole place, in the whole plane, it's a uniform velocity 10 meter per second, smooth, no change any point. Is it clear? Suppose we have this. Now, if we have an air flowing at a uniform velocity, and what I do is that I have, let's say, a plate. I have a plate. And I place this plate in the air. Okay. Now the plate is stationary. The plate is stationary. Previously, when there was no plate, it was a uniform velocity, same velocity at all points. Same velocity means no velocity gradient. Velocity gradient is change in velocity. So at any point, the velocity was 10 meters per second, so no velocity gradient. But now, when I put a plate which is stationary, now this plate is going to give some disturbance because the fluid was flowing smoothly with no velocity gradient, and now you have something in the path which is stationary. Okay? Now, there is a concept that if you have something solid, so fluid moves in layers, so the layer of fluid which is in contact with the solid body will be at the same speed of that of the solid body. So if my solid body is stationary, then the fluid, the air, the layer of the air which is in contact with this surface will also be stationary, right? Now you know that fluid moves in layers, and within the layers you have some resistance between the layers, and that generates the viscosity. That's the resistance between the layers causes the viscosity, right? And you have the shear, when you have the resistance between the layers and the layers are moving at a different velocity, then you have some shear resistance, shear friction between the layers. Okay? So now the thing is that, so the fluid which is in contact with the surface, since this plate is stationary, so will be at will also be stationary. The fluid layer in contact with the surface will also be stationary. So zero velocity, but everywhere it is 10 meters per second. So what happens is that the layer above this layer will be at slightly greater velocity, maybe at 1 meter per second. Then a layer above this will be at 2. Then a layer above this will be 3, 4, 5, 6, 7, 8, 9, and then it is like the whole, all 10, 10, 10, 10, 10. So now within this field, within the space, there is a velocity gradient. Previously, when there was no plate, everything was 10 meters per second, no velocity gradient. Now there is a region where the velocity is different. Okay? Now there is a region where the velocity is different. So that was the flow here. All 10 meters per second. Okay? You put a plate in the path, stationary. Okay? So what happened is that you have a layer of fluid which is at 0 here. Then above this a layer which is at 1. Then above this a layer which is at 2. Above this a layer 3, 4, 5, 6, 7, 8, 9. Let's say the final layer is at 10. And then everything here is 10. Is it clear? So, but this region forms a region where you have velocity gradient, velocity changing. Okay? This velocity gradient is because of this object, because this object is coming in the path of the flow with a different velocity. If suppose this object was also moving at 10 meters per second, then there was no velocity gradient, because the air was at 10 meters per second, this object is also at 10 meters per second, everything is at 10 meters per second, no gradient. But now, since this object was stationary, so you develop a region where you have a velocity gradient. And that region can be seen within a boundary. So there is a specific boundary for the region. At the boundary, the velocity could be considered as the same as the outside velocity. Okay? But inside this boundary, inside this covered region, there is velocity gradient. Velocity is different from layer to layer. Now this region is known as boundary layer region. This region is known as boundary layer region. We are not talking about anything about temperature. This thing might be at 25 degrees centigrade, and this body is also at 25 degrees centigrade. So the whole region is at 25 degrees centigrade. There is no temperature distribution here. There is no temperature gradient anywhere. But it's still, because this object is stationary and the air was moving, we have a specific region where we have a velocity gradient. Okay? That region is known as boundary layer region. That region is known as boundary layer region. So we call it velocity boundary layer. We call it velocity boundary layer. Is it clear? Do you understand this concept or not? Okay. So if I try to develop, okay, if I have an object here, any object, it will have a leading edge and a trailing edge. Okay. Now the boundary layer that is developed will have a thickness. Okay, it will have a thickness. The region will have a thickness over which within that region the velocity gradient exists. Okay. Now that thickness will always be 0 at the leading edge and will be 0 at the trailing edge. Now do you have the concept of the leading and the trailing edge? Okay. So leading edge is the edge which leads, which is in front. Okay. So if I have this object and the flow is like this, then this is the leading edge, this is the trailing edge. If I have the object like this and like this is the flow, this is the leading edge, this is the trailing edge. If I have the object like this and the flow is like this, this is the leading edge, this is the trailing edge. If the flow is like this, this becomes the leading edge, this becomes the trailing edge. So the boundary layer thickness always is 0 at the leading edge, but then it keep on increasing, okay, and keep on increasing until it reaches the trailing edge, right? Now suppose that the velocity of the free stream is v infinity. Okay, velocity of the free stream is v infinity. Okay, sometimes it's said v infinity, sometimes it is said u infinity. It depends. It's the same thing. Okay, and this is the stationary object. So what will be its velocity? 0. Okay, so the velocity at, suppose if I consider the velocity at the surface, so what will be the velocity at the surface? Velocity at the surface will be also be 0 because the object is stationary, right? So if I want to know what is u upon u infinity at the surface, so u is 0 at the surface, so u upon u infinity will be 0 at the surface. Now as you move up, as you move towards the boundary layer, the u will increase. So it was from 0 to 1, 2, 3, 4. So the u upon u infinity will also increase until you reach the boundary layer. At the point when you reach the boundary layer, what will be the value of u? It will be u infinity. So u infinity upon u infinity will become 1. So the velocity gradient or the velocity ratio u upon u infinity within the boundary layer varies between 0 to 1 at any point. So here 0, here 1, here 0, here 1, here 0, here 1, right? Okay. And after that it is all 1, 1, 1, 1, 1, 1. After that it is all 1, 1, 1. Okay. Now this thickness is also varying. The thickness of the boundary layer is 0 at the beginning, but it keeps on increasing as you move away, as you move from leading edge to the trailing edge. Okay? And this thickness is known as boundary layer thickness, delta. Okay? Now boundary layer thickness, if you want to know where is the boundary layer, okay? Suppose you have an instrument through which you can determine that what is the velocity, okay? Okay, so here if you put the instrument, it will give you velocity u infinity. Here also u infinity, 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 u infinity. Then if you are finding, suppose that you are finding u upon u infinity, so here always give you 1, 1, 1, 1, 1, 1, 1, 1, 1. Then slightly once you enter into the boundary layer region, it will give you 0.99. That is the point when you know that now you have entered into the boundary layer. Okay? Because this is a velocity boundary layer region, there is a change in velocity, you cannot see it with your eye. Can you see it? You cannot see it with your eye, it's the air. Okay? So how would you know that where is the boundary layer? Okay? So if suppose if you have an instrument which is giving you u upon u infinity, so it will give you u upon u infinity all 1, 1, 1, 1, 1 until you enter into the boundary layer region, and then it will give you 0.99. So that is the point when you actually know that now you have entered into the boundary layer, right? So normally the boundary layer thickness is determined for u upon u infinity equals to 0.99. Actually boundary layer exists at u upon u infinity equals to 1, but you will only know when it enters into 0.99. Otherwise everywhere outside it's 1. Okay? You will only know that now you are at the boundary layer when it becomes 0.99. Otherwise all upside it's 1. Okay? So normally the boundary layer thickness is determined by del. Del is the boundary layer thickness, this thickness, which is changing. Okay? So this thickness is determined for u upon u infinity 0.99. Okay. If I want to draw the velocity profile, so how the velocity profile would look like? So this is my object. Here the flow is coming. There is the boundary that's the boundary layer. Okay. So at any point, suppose if I consider this point, at this point velocity here is 0, then the velocity keep on increasing until it becomes maximum, which is u infinity. So that's how your velocity profile would look like. So this is u, this is your u infinity. So u starts from 0 until it becomes equals to u infinity. Okay, and this is the shape of your velocity boundary layer. This is the shape of your sorry, not the velocity boundary layer, this is the shape of your velocity profile within the boundary layer. That's the boundary layer. Within the boundary layer, that's the velocity profile. Is it clear? It was given as a short question to the students. Okay, I did not give this thing. I just gave the object and the boundary layer, and I said that draw the velocity boundary layer. So they had to draw it.
So there is a specific point? Or just,
yeah, I mentioned the point. Draw the velocity boundary layer at point A. Okay, so what they had to do is that's it. Okay.
Is there only mistake?
Huh? Yes, there was some. I tell you where they make the mistake. I will tell you. Huh?
I think no one thought it will.
No, I told the students that this thing can come, but I will tell you where they made the mistake. First of all, I flipped the picture. So if they had to make the boundary layer, they have to turn the page upside down, because if they have to make the velocity profile, they have to turn the page upside down, because I put the boundary layer like this. Okay.
So the maximum is at the.
At the maximum is here at the bottom. Okay.
The same.
Just the same, but okay. But the thing is that they had to turn the paper upside down to actually, and not just this trick. There was another trick, and you don't know my head actually. So, anyways, first of all, do you understand? This is the boundary. This is a velocity profile. This is what? Velocity profile inside the boundary layer region. How do you know this is the boundary layer region? It's written here delta. Delta means boundary layer thickness. So that's the boundary layer region. And this is the velocity profile. Okay? It starts from 0, become maximum. Okay? If I want to draw it on the downside, then at this point it starts from 0, flow is in this direction, so then it should rise and become maximum. Okay? Okay. Is it clear? Okay. So always consider like this. Okay, if somebody draw it in the other way around, that will be wrong, because the flow is in this direction. Flow is in this direction, so it starts from 0, become maximum in this direction. Okay?
I don't have feeling it's coming.
You know, there is a shaitan here, big one. So who always think that, what should be done? Okay. So anyways, so we have the free stream. Above we have all the free stream. Okay, this is the boundary layer region. This is del. Del is determined at u upon u infinity equals to 0.99. I think I have explained everything here. These formulas you have gone through in fluid mechanics many times. So, okay, so don't need to go through them.
This force drag, right?
Yes, drag force. What is the CF? Coefficient of friction. Coefficient of friction. Okay. Okay. Yeah, coefficient of drag is also there. Good. Okay. Okay. Now the thing is that you understood the velocity boundary layer. Okay. And the reason why the boundary layer was there, because there was disturbance in the flow. Okay. There was disturbance in the flow. That's why there was the boundary layer. Okay. Now suppose we have a case
Why you making this assumption? Why you making this assumption?
Which assumption?
That the flow is at the beginning is not just one direction and uniform.
I couldn't understand what you.
The direction of the flow.
Yes.
Why is it uniform? In real life it's uniform.
And generally, right now we are trying to understand what is the effect of any disturbance in a uniform. And generally, we don't have uniform throughout. But if there was a uniform, then what will be the effect of a disturbance in the flow? We are trying to understand the boundary layer. Okay, develop. Okay. Now suppose now we have a condition like this, that we have an air flowing. Okay, and this is at 10 meter per second. Okay, velocity u infinity per second. Now we have a plate here, and the plate is also moving at 10 meter per second. Okay, now no velocity disturbance, because everything is moving at the same velocity, no velocity gradient. Velocity gradient will occur if there is some velocity change, if the thing was stationary. Okay, so will there be any boundary layer here? No boundary layer here. Boundary layer would occur if there is a velocity change. If this is moving at a different velocity than this, if this is stationary in a moving air, or suppose if the air is stationary and something is moving, there is a velocity distribution, there is a velocity gradient which will cause the disturbance, and the boundary layer will be developed. But if everything is moving at the same speed, now there will be no boundary layer. Now suppose that the temperature of this air, T infinity, is 25 degrees centigrade. Okay, and suppose that this plate is at temperature, the surface of the plate is at temperature T 100 degrees centigrade. Okay, Now there will not be any velocity profile. There will not be any boundary layer, but there is going to be a boundary layer for the thermal system, because the air is moving at 25 degrees centigrade and air will be in contact with this surface, and the surface is at 100 degrees centigrade. Okay? So at the surface, the layer of the air at the surface will be at 100 degrees centigrade, and then above it the temperature would be a little less, then above it temperature would be a little less, and then so because of this plate, so suppose that we have air here at 25 degrees centigrade, and if I put a plate at 100 degrees centigrade, will the whole room become 100 degree? No. There will be a small region where the effect of this 100 degrees centigrade will be there. Okay? But after a certain region, everything is 25 degrees centigrade. Okay? So there is a boundary layer region here as well because of the thermal gradient. Now this boundary layer is not because of the velocity gradient. This velocity gradient, this boundary layer is because of the thermal gradient. Okay? So if I have a plate here at 100 degrees centigrade and the air is blowing at 25 degrees centigrade and the plate is moving at the same speed of the air, there will be no velocity gradient. But if I put my hand anywhere in the air, I will feel 25 degree. But if I come closer to the plate, now my hand will feel a little hot. Until I touch the plate, it will be most hot at the surface. So there is a specific region where the effect of this temperature disturbance is there. This is a temperature disturbance. Everything was 25, you put something here 100 degree. That's a disturbance. Because of this disturbance, there will be a region which will be affected. And that region will also have a boundary. Same concept. So you will also have a boundary layer for this region. And that is known as thermal boundary layer. Is it clear? So now that is known as a thermal boundary layer. So a boundary layer will be developed in the same fashion for the region. Okay? And this boundary layer is known as the thermal boundary layer. It is represented by del T. If the T was not there, then it was the velocity boundary layer. If the T is there, then it is the thermal boundary layer. Okay? And the thing is that here the temperature is, so if let's say if I want to know the temperature profile, okay, at this point, okay, so temperature will be maximum at the surface, say it's 100, and then the temperature keep on dropping, but it will not become 0. It will become T infinity at the boundary layer. Okay? So it will keep on dropping until it becomes T infinity at the surface. So it starts from T surface to T infinity. Is it clear? That's the thermal, that's the temperature profile within the thermal boundary layer. That's the temperature profile. That's how the temperature is varying. This is the region where temperature gradient is there. Outside, no temperature gradient. That's the thermal profile within the thermal boundary layer.
Why will it make like this?
Okay, we were saying that why I didn't make it like this. It's actually experimentally proved that it is like this. And in future you will have some formulations which is going to develop, which is going to determine that it will be like this.
The most hotter won't be near the surface.
Yes, yes, yes. So the most hotter one is here, and the coolest one is here. But his question was different. His question was that it could be like this. Why it couldn't be like this? It could be like this as well. Okay, maybe it does not finish there. It finished till here. Okay, but it is not like this. It is like this, and there is a reason behind it. Okay, so we're going to go through it later in our lectures. Okay, is it clear? So the question that I gave to the students was that we have, this is the plate, okay, and this is del T Draw the velocity profile at A and thermal profile at B.
Okay.
So one.
What's the condition?
So where if I want to draw the velocity profile at A,
So we down.
so it should finish at del,
Yeah.
should not go till del T.
Yeah.
And if I want to draw the thermal profile at B, it should finish at del T, should not finish at del.
Okay, what about the condition? Stationary or
This plate is stationary, and the temperature here is Ts, here temperature is T infinity, velocity is U infinity, okay, and Ts is greater than T infinity. Here they like Ts is greater than T infinity. It's like the same thing that you have to draw, but
that's true, sir.
yeah, but students made the mistake. Why? Because when they were drawing the velocity profile, they did not finish till here. They continued and draw it like this. Okay? So they draw it like this. Wrong. It should finish till here. That's the boundary layer thickness. That's the thermal boundary layer thickness. Okay? So students did mistake. Yeah. So now I'm thinking to make the exams again, because at that time I wanted the shaitan to, yeah, it was locked. Okay. Okay. Anyways, do you understand the concept here? Main thing. Okay. Why do we have thermal boundary layer? Because if we have now consider the two things together. Suppose you have air blowing at 25 degrees centigrade and you have a plate stationary at 100 degrees centigrade. So now the plate is stationary, so you will have a thermal boundary layer. You have a velocity boundary layer, and the plate is at 100 degrees centigrade and the air is at 25 degrees centigrade. So you have a thermal boundary layer. So both the boundary layers are there at the same time. Okay, but the reason, you know, because there is velocity disturbance, because there is temperature disturbance. Okay, and they will have a boundary layer thickness. Okay, it was a conceptual thing, but it's good. Okay. Oh yeah, a lot of usage. Don't worry, your wait will be soon over. And then you will remember the time when you were waiting, and you will curse yourself. Why were you waiting? Okay. Okay, so basically, if we want to know that what is the amount of heat transfer at the surface, if we want to know what is the amount of heat transfer at the surface, so the amount of heat transfer at the surface will be the amount of heat conducted out equals to amount of heat convected. Our conduction equals to convection is the actual amount of heat transfer which is taking place. So for the conduction, you have K. If we talk about the heat flux, then it's K dava T by dava Y. Okay. Why I put here dava T by dava Y? Because temperature is varying with Y. Okay. So temperature is varying with Y. At any x, temperature is constant. So this temperature equals to this temperature, this temperature, this temperature, but the temperature variation is only in the boundary layer region, in the Y direction. It's okay. That's why it's dava T by dava Y. But since I want to know how much is the heat conducted out at that point at the surface, so at the surface Y is equals to 0. So Y is ranging from where? Y is ranging from 0 to del T. Okay. So if we want to know how much heat is conducted out at the surface, that at the surface Y is 0. Okay. So negative K dava T by dava Y is equals to Qs is equals to H Ts minus T infinity. So from this you can find the formula for H. That's it. Okay. Now the thing is that let's talk about the local and average heat transfer coefficients. Okay. You know Q is equals to H A delta T. Q is equals to HA delta T, but this H is going to vary from position to position, okay? Because this H hugely depends upon the thermal boundary layer thickness, okay? This H depends upon the thermal boundary layer thickness. So as the location is changed, the thermal boundary layer thickness changes and the Q changes, okay? So we will have a value of H here, which will be different from a value of H here, which will be different from the value of H here. So value of H will be different from point to point, okay? So at any point, the value of H at that point is the local heat transfer coefficient. Local means at that point, because again, the value of H here will change from point to point. Why it will change from point to point? Because it depends upon it depends upon the thermal boundary layer thickness, okay? It depends upon the thermal boundary layer thickness. The thermal boundary layer thickness behaves as a resistance, okay? So larger the thickness, smaller will be the value of H. Smaller the thickness, larger will be the value of S. Larger the thickness, less heat can transfer. Smaller the thickness, more heat can transfer, okay? So it behaves as a kind of a resistance to the flow of heat, okay? So the value of H will change for point to point. So, but if you want to know the value of H at any specific point, then that value of H is known as the local heat transfer coefficient. That's the local heat transfer coefficient. But sometimes we are not interested in the local heat transfer coefficient. I'm not interested that how much is the heat transfer from this specific point. I want to know how much is the heat transfer from total. So now we are not concerned about the local, how much is the heat transfer from any local point. We want to know average. Tell me an average. So for the case of average, if we find out the total amount of heat transfer, then divide by the total temperature difference, you'll get an average heat transfer coefficient, okay? So that is the average heat transfer coefficient. So we'll have an average heat transfer coefficient for a body, and we can have local values as well, okay? So how we determine the average heat transfer coefficient? The formula is this. So local heat transfer coefficient is represented as H, but if we have an average, we represent it as H bar, okay? And the formula is that H bar is equals to 1 upon surface area integral H dAs. This is the local heat transfer coefficient. So local heat transfer coefficient is varying with the surface area. As the position change, surface area change. Okay, so that's in the two-dimensional form. If it is one-dimensional form, then H bar is equals to 1 upon L integral H dx. So if this is your x, so you change the position of x, H will change. So find out the H for the complete position for point, let's say from x0 to xl, 0 to L, integrated, divide by L, so you'll get the average heat transfer coefficient. So it's just saying how to find average heat transfer coefficient, find out the local heat transfer coefficient for the complete range, divide by the complete range, okay? So that's the two formulas here for local and the relationship between local and average heat transfer coefficient. Okay. Okay, let's have a small problem right here. What's the time? 2:40. You have a lot of time. We should not reject the gift, you know. So experimental results for the local heat transfer coefficient over a flat plate with an extremely rough surface were found to fit the relationship this. As you know, h is a function of x. You change the position of x, h will change, local value. Okay? So somebody experimentally determined that for a very rough surface, flat, rough surface, h is a function of x, like this. A into x raised to the power negative 0.1. Well, this they determined it experimentally. Okay, where a is a coefficient and x is the distance from the leading edge of the plate. Okay, develop an expression for the ratio of average heat transfer coefficient for the plate of length x to the local heat transfer coefficient at x. Okay, so we need to develop a relationship between this. We are given h as a function of, so we are given this local value, h as a function of x, but we need to develop a relationship between average value and local value. Okay? It's very simple. We already have the relationship. This is the relationship. We just need to substitute the value. Okay? So we have this what? H is equals to, average value is equals to integral, so 1 upon L integral h dx. Okay? Now h local value is given here is ax raised to the power negative 0.1. Let me put the value here, ax raised to the power negative 0.1, right? Now a is basically a constant. Now here this will be actually 1 upon x. It will be 1 upon x because we want to find it from the leading edge to whatever the length x. Okay, so a is a constant. It can come out. A is a constant. It can come out. Okay. Now if I want to integrate x raised to the power negative 0.1.
Yeah, +1.
Yes. So I can integrate it as it will become +1 divided by negative 0.1 plus 1. Right. That's the integral. And this x into negative 0.1 plus 1, I can write it as x into negative 0.1 multiplied by x. I can write it like this. Right? Right, Ghazani? No? If you have x into negative 0.1 plus 1, I can write it as x into negative 0.1 multiplied by x into 1. Right? This is like this. Right? Okay. And this will become what? 1 minus 0.1. So that's 0.9. Right? What is 1 upon 0.9? Anybody has calculator? 1 upon 0.9 is what? Yeah. 1.11. Let me remove this thing and I will write here 1.11. Right? Okay. Now this x can be cancelled with this x. Right? So now we have what? We have a x negative 0.1 into 1.11. A x negative 0.1 is basically local h. So local h into 1.11 is equals to average h. Right? We wanted to find a relationship between local and average. Okay? So we determined it. Local h is equals to multiplied by 1.11 is equals to average. Yeah, this is a math question actually. So it's written here. Okay, now there's one concept which you have definitely gone through in fluid mechanics, laminar and turbulent boundary layer. Okay,
Yes.
Laminar and turbulent boundary layer. So what is a laminar flow? What is a turbulent flow? What do you know about it?
It's like, you know, the number constant. If it's less than 2,
Laminar, the fluid makes smooth say smooth.
Perfect. Turbulent means
Like disturbance.
disturbance. The flow is disturbed. That is turbulent. The flow is very smooth, calm. That's laminar. Okay. So it determines the fluid characteristic. Okay. It determines how is the flow. It defines the flow if the flow is smooth or if the flow is not smooth. Okay. This is the thing. So that is laminar and turbulent flow. Now what happens is that if you have a mean stream and you put a plate in between, initially over the plate the flow would be laminar. After some distance has passed, the flow will become slightly disturbed. We call this as the transition state. Transition state is not laminar, not turbulent. It's in between, but we can never determine whether it is laminar or turbulent, because in transition stage, part of the time it behaves as laminar, part of the time it behaves as turbulent. So it's in the transition stage, it's changing all the time. Okay? And then after that, it is fully disturbed. After transition stage is over, then it is fully disturbed, and there is a lot of disturbance in it, and the fluid is moving in all direction. Okay? So that turbulence. Most of the time, in application, we are very much interested in turbulent flows. Turbulent is a lot disturbed flow, but it allows heat transfer to be very, very quick. Okay? Suppose if you put cold water with hot water, it will mix, but if you want to mix it quickly, you will take a spoon and you will stir it. You are putting turbulence into it. Turbulence will cause the heat transfer to be very quick. And you need quickness. You want quick heat transfer most of the time in application. So we are most of the time interested in making things turbulent. Laminar looks good, but what the hell? If its heat transfer is slow, less, then it really doesn't help us much. Okay? So most of the time we are really interested in the turbulent flows, but there are many ways, or many things in which we cannot really ignore laminar flow. There are many cases where laminar flow is a reality. You cannot ignore it. No matter how much you want turbulent flow, you cannot make it turbulent in those conditions. Okay? There are many conditions. You will study. So we need to study laminar and turbulent both, obviously. Okay? But we like turbulent.
But in fluid, we like turbulent. Right?
No.
Even in fluid, not?
No, fair enough. But there are many cases where we cannot ignore laminar. We cannot make it turbulent in those cases. Laminar is easy to solve. Turbulent is comparatively difficult to solve. So that's why students like laminar more. Okay? But when you are in the industry, then you don't care whether it's easy to solve or hard to solve. You only care whether you make more money or not. So in order to make more money, you need quick heat transfer, things like that, more efficient systems. Okay, so you want turbulent systems most of the time. Recount it. Okay, the thing is that now how do we determine whether a flow is laminar or the flow is turbulent? Is it the velocity? Is it really a fluid which is moving at a high velocity will always be turbulent? Not necessary. Is it then what it is? Okay, so after performing a lot of experiments and a lot of dimensional analysis studies, okay, scientists came up with a formulation, and specifically the person who came up with this his name was Reynold. So he put the name as Reynold number, and this Reynold number is basically a dimensionless criteria to determine whether the flow is smooth or not. High Reynold number means the flow is not smooth. There is disturbance in the flow. It does not mean the flow velocity is high. It could be. Flow velocity could be high, but not necessary. Okay? And low Reynold number means the flow is smooth. Maybe the velocity is slow, maybe the velocity is high. Okay? So what is this Reynold number? So the Reynold number is basically rho v L upon mu. So in order to determine whether a flow is smooth or not, you have to consider 4 parameters of the fluid. First of all, you should know what is the density of the fluid. You should know how fast is the fluid, what is the velocity of the fluid. You should know how long the fluid has been in travel. Length is how long the fluid has been in travel, and you should know what's the viscosity of the fluid. Do you understand physically all these terms? What is the difference between density and viscosity physically?
Viscosity,
The change velocity.
viscosity is movement.
Density is the resistance to movement, flow.
Viscosity?
The resistance. The same. Viscosity.
Look, in physical terms, if I say density means how heavy is the fluid.
Okay. Yeah.
Viscosity means how thick is the fluid.
So what?
Thick. Is the fluid thick or thin? Okay. Now, many times it happens that the fluid which is thick is also heavy, but not necessary. For example, you know honey. You take honey, one box of honey, and the same quantity, you know, grease. Grease, we put it in the car or sometimes on the motor bicycle chain to make it smooth. So take grease, same quantity, and honey. Grease is more thick but will be lighter. Honey is less thick but will be heavier. Okay, so not necessary that everything which is thick is also heavy. Yeah, most of the time it happens like this, that the fluid which is thick is also heavy, but not necessary. Okay, so when we talk about viscosity, we means the thickness. How thick is the fluid? Okay, when we talk about density, we means how heavy is the fluid. So if you take the weight of the fluid, is it really heavy or not? Okay, so there is a possibility a fluid is thick but not that heavy, like the case of grease when compared with honey. Okay, and things like that. Okay, v is the velocity, how quick, how fast is the fluid, and L is the length, how far the fluid has traveled from the starting point. When it has started to travel, how far it has traveled. Okay, in connection with the surface. We are not talking about a fluid traveling alone, free stream. In connection with the surface, how long it has traveled. Because when it connection with any surface, then there are some forces that starts acting on it, and which tends to make the flow disturbed, not smooth. So that's why initially the flow starts smooth, and after traveling a certain distance, it becomes turbulent. Okay, because there are certain forces that starts acting on the fluid. The fluid can resist for a small period of time. After that, the fluid becomes turbulent. Is it clear? So these are the parameters which determine that whether a fluid is smooth or the flow is not smooth. Okay, not necessary. Sometimes the velocity high. Yeah, many times what happens that if the velocity is very high, so the Reynold number will be high. If the velocity is less, the Reynold number will be less. But it's not just the velocity. For example, lava. You know, from mountains, lava come. Do you see the speed of the lava? So slow. But lava is highly turbulent. It's not smooth. It's not just the velocity you have to consider, the weight and the viscosity. Okay, the lava that comes out of the mountain, moving very slow, but it is highly turbulent. It's not laminar.
So not, you said before that you're interested in the turbulent, but you need the turbulent which is very fast or the velocity is high?
We need turbulent, irrespective of what's the velocity, because it is the turbulent which increases the heat transfer.
Even if velocity is
Even if the velocity is slow, but it depends. What are you using? Where are you using? Okay, you're using water or air or some oil or what? Okay, depends. Yeah, lava is slow, but you cannot use lava for heat exchangers most of the time. Okay, so the thing is that we are limited. We are limited many times in our applications. But anyways, do you understand the concept of Reynold number? What are the parameters over which it depends? Okay, what does the Reynold number mean? It determines the smoothness of the flow. How smooth is the flow? Not necessarily. It doesn't necessarily mean velocity. The velocity is a very important factor, but there are other factors as well: density, viscosity, how heavy is the fluid, how thick is the fluid, how much the fluid has traveled in conjunction with the surface. Okay. So anyways, that becomes our Reynold number, and there is a critical Reynold number. The critical Reynold number for an external surface, if the flow is over a surface, not inside a pipe, over a surface. Okay. For that surface, the critical Reynold number is 5 × 10⁵. So below this number, we consider it laminar, whether it is laminar or not. Maybe it is in the transition range, but we will still consider it laminar. Above this range, we will consider it fully turbulent. Okay? So we do not consider anything for transition. We consider for laminar turbulent. Okay?
the value is before 2000.
That's for the flow inside a pipe. This is flow over the surface. Okay? There is a difference between internal flow and external flow. This is chapter 6. Chapter 7 is for external flows. Chapter 6 is for internal flows. You will understand the difference between internal and external flows when we come to those chapters. Okay? Even these numbers, it's okay, it's written here, but it's just as an introductory, it's written here. You will understand these numbers more in detail when you come to that chapter. Is it clear? This is just the last slide. This problem we will start tomorrow. Okay, so this slide explains you that how is the heat transfer coefficient varying along the distance, along the length. Okay, so as I told you, this initially it is a laminar flow. So in the laminar region, heat transfer coefficient drops. Why it drops? Because the boundary layer thickness keep on increasing. When the boundary layer thickness is increasing, this is kind of a resistance to heat transfer. So heat transfer coefficient will drop. However, in the transition range, there is a significant hike because it now moves from laminar to turbulent, and turbulent has an inherent characteristics that it increases the heat transfer significantly. So as it enters into the transition region, so that means it is moving from laminar now to turbulent. So while it is moving from laminar to turbulent, there is a significant rise in the heat transfer coefficient. Now at this point it becomes fully turbulent. Now once it becomes fully turbulent, now again the boundary layer starts keep on developing like this. Okay, so again as the boundary layer is increasing, so the heat transfer will again start decreasing. Heat transfer coefficient will again start decreasing. Is it clear? So because of the boundary layer increase, heat transfer decrease, then from laminar to turbulent jump, there is a hike in the heat transfer coefficient, then again boundary layer further keep on decreasing, so heat transfer coefficient decrease.
Shouldn't be increased in the last stage because it's turbulent?
It is turbulent, so it's already increased, but now within the turbulent region, the boundary layer is further increasing. Okay, so now it is fully turbulent. That's why there was the hike until it became fully turbulent. But now once it becomes fully turbulent, now while being fully turbulent, boundary layer is increasing. Okay, so the heat transfer coefficient started decreasing. This is a graph which I can ask you to explain in the same way the way I explained it to you right now. Huh? Yeah, yeah. In a reflection way, yes. So I'll put a mirror here and then I'll put everything upside down. Okay. Anyways, do you understand this explanation or not? Because I can ask you to explain exactly these things the way, why is this H decreasing? Why was there is a hike here? Then why further H started decreasing again? Okay? Because it moves from laminar to turbulent. In some transition region, it starts moving from laminar to turbulent. Okay? So you will have the video so you remember maybe. So if you don't remember, then okay, that's it for today, inshallah. From tomorrow, we will start from this slide and we can